Hello, everyone, and thank you very much for the opportunity and the invitation to give this talk. Well, as you can read, I'm going to talk about bispectral functions and some results related to them. Many of you already know what bispectral functions are. Actually, you know even better than I these bispectral functions and properties and the history. And anyways, I'm going to define them. But before, I would like to present one of the motivations behind this notion of bispectrality. So Claude Shannon considered many problems, but one of them in his works in the late 40s, actually he had two papers in the 48, and one of the questions was related to the following situation. Let's assume that we have a signal, a noun, a function f of finite duration, of course, and we are going to assume that the support of this function in terms of the time is a compact interval, minus n. And we are only getting some of the frequencies of this signal. So we are only getting a band. This is the band limited property of the problem. So for the Fourier transform, which I'm denoting by this f capital F applied to f, we are only getting the values that it takes in this compact support. So the question is, let's assume that we know this Fourier transform, but only in this interval, and we know that the function f is supported in minus n. So what's the best we can do to recover the most possible about the original function f? So the thing is that this will lead us to consider an integral operator. Sorry for that. So essentially we have, let's say, the space L2 of R. Well, let's assume that this is an capital L. The space of square integrable functions. So we have inside this space, we have our function f. And we have the Fourier transform. And we can also consider the operators that consist of multiplying by the characteristic function of the compact interval, let's say n and omega. So the Fourier transform of f is going to give us a function, of course, this fashion, more or less. But, well, since the function is compact supported, we can write this down as the integral between minus n and n. And of course, we are only considering the values of this Fourier transform in the interval minus omega. So this is going to be our data. This is our function g. We can call these compositions of operators E. This would be E applied to f, evaluated in the variable y. So the thing is now that we will need to understand the singular values and vectors of this operator E. So for that, we are going to consider also the E star, and in particular, we will have E star E applied to F, in, let's say, Z. It's going to be double integral between minus omega and omega and minus n of fx the exponentials. And of course, I'm missing one scalar here, and sorry for very unclear presentation, but I was missing scalar 2 pi. Of course, E star involves the inverse of the Fourier transform. And well, this is the operator, and with a little bit of manipulation, we can rewrite this as 1 over 2 pi and the integral between minus n and n fx times the integral between minus omega omega of the product of these two exponentials. Sorry, this was a typo here. We need a this is a set. So, well, this is the integral operator that we are going to try to study and search for the eigenfunctions, eigenvalues, etc. Well, the thing is that this kernel is a sinc kernel, but this is going to simplify a little bit the expression, but still we are dealing with an integral operator. And this very setup can be reproduced in a very more general context. Instead of having an interval, we can think in a compact set, let's say A and B. This would be the minus n and minus omega omega, and the function now, the signal, this little f, could be a multivariate function. I'm repeating Fourier transform, but we could think in a more general transform. So the situation is going to be more or less the same. So we have this signal supported in a compact set A, and the Fourier transform is known to us in a compact set B. So we have these two properties. The Fourier transform of f times the phi b is the known, and we also know that phi a, I mean the characteristic function of the compact set A times the function f is again the function f. So combining these two, we have our operator E, which is the analogous of the operator E that I wrote before. So if we know G and we know how to build E, how we recover information about F? Well, as I said, we need the singular vectors and values of this operator E. In other terms, we are going to study these two operators. We are dealing essentially with a problem of a double concentration problem. Well, the thing is that, for instance, in this original case, which I was describing at the beginning, so the set A was this interval, B was this other one, and here we have this sinc kernel. Was solved later, not by Shannon, but by Slepin and Landau and Pollack in different works. The problem is that you cannot attack this problem directly. So if you want to understand the eigenfunctions of this integral operator, you can think of this operator as a global operator. It is essentially impossible. Even numerically, you can have some kind of, for some cases, some approximations to the eigenfunctions, but you cannot, in general, control the error you're having. What happens, some people call it a miracle, this commuting miracle, is that for some reason they could find a differential operator, P, which was symmetric with simple spectrum of order 2, and it commutes with our integral operator. So given all these properties, all the eigenfunctions of T are going to be eigenfunctions of the operator E star E, and in general study the eigenfunctions of a symmetric second order differential operator is much easier. In that case, the operator was given by exactly this expression, and that was essentially the way to solve it. You can explicitly find the eigenfunctions of this operator, and they are going to be the eigenfunctions of the integral operator, and that's it. The same occurred with Bessel kernels and Airy kernels. So since then, this kind of results were reproduced in different conditions, different setups. For example, we can mention the generalization to higher dimensions. And later, well, instead of considering the Fourier transform, you can think in the Fourier series. So essentially, you're going to have, I'm going to call it F, capital F still. And well, now the signal, let's say it is little f, but the integral operator, or the global operator, capital E, is going to be given by something like chi omega f chi n. Now, this chi n is just a truncation in the sequences here. So chi n applied to a sequence here is going to give you back a vector. Then you have two different operators as before, but now these operators acting in different spaces. E star E, sorry, I'm having some technical issues. E star E and E star. So this operator E goes from sequences to functions. So this operator goes from sequences to sequences. And if you interpret this as well, the conversion of a sequence into a vector. This essentially is going to be a matrix. So this operator goes from this L2 to itself, but you can also interpret it as a matrix. And well, this is very similar to the previous one. This is an integral operator. In any case, these both are global operators. And well, you have all the corresponding analogies to the previous cases. Later, it's worth to mention the work of Grunbaum, Longe, and Perstat. They worked on some symmetric spaces in which they had the action of some non-abelian groups. Then Perstat did some work for classical discrete polynomials. Then Perline worked for working in some conditions of finite time and band limiting. So here the functions were defined over a finite set. And then, well, there's some works by Grunbaum trying to advance and give some light over these. As a comment, I here mentioned that, well, this particular work found some applications like 2 decades later. But at the end, the common property for these functions to give this very special phenomena of giving this integral operator that admits a commuting differential one, apparently is bispectrality. So bispectrality is defined by this means. We need a function in 2 variables, and we have an operator L and D. L is an operator. I put this subindex just to emphasize that L is acting on the Z variable, and our function is an eigenfunction of this operator, which is an operator in Z, and the eigenfunction depends on the other variable. So you can call this the spectral variable. And for D, you have the reverse situation, right? Of course, here I'm talking as these 2 variables were continuous, but you can have the situation where one of them is discrete. So you will have the situation of for instance, orthogonal polynomial satisfying a second-order differential equation. And these kind of situations were considered from this angle by Grunbaum and Hein. I'm pretty sure that you understand this better than me, but just in case. So one of these variables could be a constant, a discrete. So let's say that D is a differential operator. So you have for the orthogonal polynomials, you have a 3-term, and I'm going to call this 3-term actually L, acting on N, and the polynomials are depending in X and N. So this is a 3-term, and we know that orthogonal polynomials satisfy this 3-term, and the eigenvalue is going to be just X. And of course, well, if they are, for instance, classic orthogonal polynomials, they are going to also satisfy a second-order differential equation. And you're going to have an eigenvalue. This is wrong. This is very, very wrong. It should be set. Eigenvalue lambda, depending on the other variable, spectral parameter, n in this case. So, well, classic orthogonal polynomials are a particular case of bispectral functions. And of course, later I will mention a little bit more about this, but instead of just thinking in this kind of properties, when you have a function here, you can think also functions, let's say C, and the operators such that when you apply them in one variable, you obtain the same to applying another operator in a different variable. So instead of just having these kind of equations, you can think in more complicated things here. And this is going to lead to the notion of Fourier algebras and bispectral algebras. Well, I believe that one interesting example to show, just to illustrate how this works, maybe this example that I'm showing you now, is matrix value orthogonal polynomials. I mean, we are in a discrete and continuous setup, but also taking matrix values, so we have an extra complications. We work in some of these kind of setups with Pacciaroni and Grunbaum. And at the end, we have still the same commuting operators phenomenon. So, well, the thing, sorry, there we go. So the thing is that we have this W, which is a matrix way in an interval AB, and we are going to consider matrix orthonormal polynomials given by this expression Q sub K. And our two spaces now are going to be these two, this sequence of summable matrices, square summable matrices, and L2 in W. So these are the matrix valued functions that are of square integral. I mean, you need this condition. And we are going to have the map F, which is the analogous to the Fourier transform for the other cases, which gives you these functions when applied to these sequences, and the inverse, the dual. And this is a unitary map, so the inverse is a dual and is given by this expression. You have a function, and well, you can build this sequence given by this expression. So as before, you are going to deal with two spaces, and here we are going to have the limiting operator, which is the one that is chopping the sequences in this space. So you're going to, after applying this operator, you're going to have these vectors, and on the other hand, the band limiting operator, which is similar to the previous that I mentioned, is just multiplying by the characteristic function in this interval, instead of considering AB, A omega. And well, the building of the global operators is the same. Again, we have this combination, He omega F applied to F is our known. We also have this property, so the integral operator is again called E, which is made from this combination. And again, we need to understand the singular vectors and values of this integral operator. And for that, we need to study this operator and this one. Well, as I mentioned before, this operator is essentially a matrix now we have a matrix in which every entry is again a matrix. And in this side of the problem, we are going to have an integral operator taking values in matrices. So one of these operators is a matrix given by this expression. Every entry is of this form. Remember that everything here is again a matrix. And the other operator, the integral operator, has a kernel given by this. This kernel can be simplified similarly to when you simplify and obtain the sinc kernel. Well, you can use particular properties of these orthonormal polynomials and simplify this sum, so the things are more easy to work with. So on one hand, we have this matrix made of blocks, and to build a commuting operator that is going to solve the things, what's the analogy to the differential here? Well, it's going to be a difference operator, and we, in the previous cases, we had these order 2 symmetric differential operators, where here we are going to have symmetric 3-diagonal matrix L, and of course we still require it to have simple spectrum. And surely this is the crucial property, commuting with our matrix M. So M cannot be studied directly, but we can attack through this L, which, for the same miracle, let's say, is going to exist. So we have to find or build this matrix L, which is going to solve our problem. And the eigenvectors of L are going to be, of course, the eigenvectors of M as well. And in the other side of the problem, so the continuous side, we have this integral operator given by S. So for each value of these parameters n and omega, we have to find a self-adjoint differential operator T with simple spectrum commuting with it, as before. The first example in which we jumped in with Grunbaum and Pacciaroni was a very particular example of matrix value orthogonal polynomials of size 2. So every entry here is going to be a block, 2 times 2 block. These were Gegenbauer orthogonal polynomials in a matrix version. So we had this global operator given by a matrix, and every entry is given by this expression. The interval here was -1, 1. So after this truncation, this band limiting, we have only the interval -1 omega. And we find the commuting operators. Here the dimension of commuting operators, because, well, it is a space, and the dimension was 3. Here I'm showing you the simplest one. Every entry of this commuting operator, which is not that is not 0, is a block of this way, or this fashion. And well, AK, BK, CK are given by very ugly expressions, but it doesn't matter. So the thing is that we have this 3-diagonal matrix commuting with our matrix M. For instance, for n equals 3, we have this n+1 times n+1 matrix, whose entries are blocks of 2 times 2. And we had to prove for this very particular case in a special way that the geometric multiplicity of the eigenspaces is 1. So that is going to guarantee that they share the eigenvectors. And that was pretty much it. But I would like to repeat something that we put in that paper. It's a numerical computation with a little bit of an exaggeration in some sense. So we ask a computer to give us the eigenvectors of M for this particular size, and capital N equals 3. So we ask the computer to just round up the approximation of the entries. So the eigenvalues are given by these, the eigenvectors of M are given by these columns. And actually, well, if you build the diagonal called capital lambda with the corresponding eigenvalues, so you can check that this is very similar to the matrix 0. But on the other hand, we consider with the same program and the same conditions, we consider the eigenvectors of L, and again, we build a matrix with these columns. So, well, we are normalizing these eigenvectors, so these are going to be orthogonal matrices, essentially, and up to permutation. And before in the next step, we check that the eigenvalues essentially were 1 for M, which is showing actually that there is something very, very wrong. For L, instead, the eigenvalues were very different to each other and very separated. And in particular, when you do this product, you should obtain the identity up to a permutation. And well, the first column is a 1 and a bunch of very small numbers, let's say zeros. Again, we have a 1 and a lot of zeros. Now we are going away from 1, and suddenly we cannot even decide which one should be the 1 and which one should be the zeros. Well, and this is just to prove that having these 3 diagonal matrices is a lot better than just dealing straightforward with M. On the other side, we can talk a little bit about the continuous part of this problem. So we have this integral operator given by this kernel. This kernel is a sum, which we would like to simplify in order to solve and find this commuting in second order differential operator. So we are seeking for an differential operator T defined in this interval that commutes with our integral operator, and we need it to be symmetric in this interval, which means that, well, it satisfies this for this new inner product. We are considering a smaller interval. So, well, of course, I'm skipping a lot of the details, but essentially, one of the things you want is that the operator you are building has to, when applied to the kernel, has to be essentially the same. The conjugation, this star is inside and outside, but essentially you want the operator acting in one of the variables to the kernel is the same to act in the other variable. And for that, we use, in the same way that you can obtain the sync kernel in the original case, given the kernel as an integral. Here we have the kernel given as a sum, so you can pass that to the quotient, and you have this expression thanks to the Christoffel-Darboux formula. This, of course, appeared before for scalar value orthogonal polynomials. But well, here is important the order. As you know, the matrices do not commute, so we make use of that formula. We also have this differentiation formula for these particular polynomials with a lot of coefficients that I'm not going to detail. And finally, we get the differential operator of order 2, symmetric, commuting with our integral operator, given by this expression. Of course, it depends on the parameters omega and n, related to the time limiting and band limit. So later, we realize in a different work that we can solve simultaneously both sides of this problem. So we have our matrix as an operator in one space, and we have our integral operator acting in a different space. And of course, you can conjugate an operator and moving it from one space to the other. So we are still considering this integral operator, but now instead of the matrix, we can consider this operator. So we have two global operators which are different, but they are in the same space. And we can rewrite the operators in that way. So this wiggle means that we are conjugating by the map F, capital F, the operator below the wiggle. So essentially, we solved the problem of finding a commuting differential operator of order 2 for any family of orthogonal polynomials satisfying a second order differential equation. And for the case of matrix value orthogonal polynomials, we need an extra matrix here in blue that sometimes you can get and sometimes you cannot get. That's something to fully understand still. And well, here I'm writing this operation two different ways, just because maybe someone of you can see a more or less familiar expression. So one of the theorems says that the differential operator that we build commutes with both of these integral operators simultaneously. And when it is applied to our family, bispectral family, essentially you have this very explicit action, and well, and xk, yk, zk are given in a very specific expressions. So if you conjugate the operator, you're going to have this three-diagonal matrix L, and the expression of this L, which is the one that is going to commute with the global operator M, is given by this three-diagonal symmetric matrix. Sorry, Hermitian matrix. In the few minutes I have, I would like to mention some very recent results in joint works with Kasper, Grunbaum, and Yakimov. So this is in the context of continuous and scalar value functions. Wilson in the 93 realizes that a very clever way of approaching in a deeper way this problem was to classify these bispectral functions according to the rank, which is the greatest common divisor of all the order of the differential operators that have this bispectral function as an eigenfunction. So he classified all the rank 1 bispectral functions, and essentially they are given by this expression. I mean, all of them are going to be given by this, and they also satisfy this other property. So essentially, this is the way you construct the bispectral function, and here you have the Darboux transform involved. So, well, I will jump most of the details, but essentially all the examples studied to this point were particular cases of integral operators with kernels given by this expression. Here, this is the Wilson adjoint, but we don't need to complicate the notation here. But you can, in general, you can think of this as a complex conjugate. So the first result we got is that if you can understand well enough this Fourier algebra of all these differential operators R that apply to the bispectral functions, give you again the bispectral function, but with the action of another operator in the other variable. So once you understand very well this algebra, you can guarantee that if you build the integral operator, you will find here an operator that we call again T, that in general will not commute with the integral operator, but it will reflect it. Reflect meaning that they almost commute. There is an involution involved in the middle. Essentially, there is a change of a sign in one of the variables. So the result is, well, if you have an integral operator with a kernel of this way, you can find always this reflecting differential operator, and you can also guarantee that the order of this differential operator is bounded by this constant in terms of the degree and the codegree of the bispectral function. So, well, we restate that theorem in a little bit more complicated theorem, which now is in these terms. And here you have the more usual expression for the kernel. But essentially, the theorem is an adaptation of the previous one. But, well, here there are two involutions, some conditions which are very technical, but in general, they're satisfied. But, well, we have this reflecting thing. Always we can build this reflecting operator. We don't only guarantee the existence, but we also give the algorithm to build this operator inside this generalized Fourier algebra. So the thing is that from that we can find a commuting operator by the meaning of applying some rotations to one of the variables. So if you can find the reflecting operator, then you can build a commuting operator. So essentially we build a systematic way of guaranteeing, checking if you will have or not this commuting operator and what's the degree, the order of the operator, and also how to build it. So this was the first non-trivial example in the paper by Deutstermann and Grunbaum, which, by the way, in this paper of the 86, they introduced essentially this notion of bispectral functions or bispectrality. The expression of this bispectral function is exactly that one, but if you build the integral operator, you will not find a commuting operator of order 2, and you will not find either a commuting operator of order 4. But you can build, according to our method, a commuting operator of order 3, which is not self-adjoint. But of course, you can build a self-adjoint operator just by considering this new operator of order 6. And also, you can find a different operator of order 6 of this form. So there is not only one. I mean, you can have 2 linear independent operators of order 6. And this is the self-adjoint way of writing it. And the factors are given by these expressions. So, well, this is just to try to show how this new result, which is very general, also applies in a very concrete and quick way to problems that before were essentially very, very hard or almost impossible to handle, right? I mean, if you don't know what are you looking for, it's very hard to find these kind of operators. Well, that's pretty much all. Thank you very much. And